Darn it! I was trying to sell advertisement. Yeah, drink this energy drink. You'll do better in your final exam. You too. Uh, uh, it depends on whether you're buying the 50 pack or the 100 pack or the 200 pack. I am I am not gonna repeat what you just said because I don't want other instructors to get the same idea. Oh, you'll be surprised. Oh, yeah, yep. Well, by the time you guys realize that you cannot find a job because I did such a poor job of educating you, it's not really traceable back to me anymore. Be- it's not traceable back to me because you'll be graduating from a 4-year university. The blame is on the 4 year. It's not what you took, like 2 years before you transferred. The pandemic is one, AI, and then so the last one you're gonna put the blame on is your professor. I don't know where the AI is gonna go, but I think it's gonna plateau because they run out of material to train the AI at this point. So what they're really doing, well, then they become a rabbit. Okay, do you know what rabbits do? They eat their own poop and they multiply like crazy too. But they are food on in somebody else's tummy. Ah, okay. So what we're gonna do today is I'm just gonna finish implementing your homework assignment, and then we'll move on to the final exam. Okay, so we'll go through the final exam, and I can do my best to share with you, what I would do as a student to prepare myself for the final exam. Like what I think might be helpful, um, but you kind of have to think it for yourself too, because the way I understand material may not be the way that you do. The way that I process items may not be the same way that you do. So you kind of have to work out what works for you. I can only make suggestions based on myself, unfortunately. All right, so let's go ahead and implement the function, and we'll focus on the function because everything is already given to you. So the only thing we are left to do is function f in this case. And there's a little stub here, okay? Obviously, you can keep the halt instruction as long as it is after the return instruction sequence. Then it's not going to bother anyone. All right, so as usual, what I like to do is to look at the call frame, look at the invocation frame, and try to figure out, what is where on the stack, or what is where in this call frame. The last item on the stack, or the one that has the highest address, is going to be the last parameter, which is pn in this case. So pn is going to be at the highest location in the call frame, and then the first parameter, which is ppn, is going to be right under that, and then there's the return address. These three items are pushed by the caller. So one thing, so I'm just kind of interleave my suggestion for the final exam with the solution of this homework assignment. The caller callee agreement is really important. Okay, so that means you can do one of many things, okay, or do multiple of those multiple things. Whatever you do, you need to make sure that you fully understand the caller callee agreement. You can print out the one that I have prepared, okay, and bring it with you, just verbatim. Assuming that you have read it and understand where to find the material, it's all good. You can rewrite that whole thing in your own words, in your own organization, with your own pictures. Bring that with you. Okay. You can even upload my material to ChatGPT and ask ChatGPT to give you a condensed version so that you can kind of have a shortened version where things are easier to find. And ChatGPT is actually pretty good with making quote unquote pictures out of ASCII text. Okay, so you can even ask ChatGPT to give me a pictorial representation of what is on the frame and use this C code over here as an example. It would do that. Okay, now you do have to double check because there are a few things that it can confuse about because there are standards that are slightly different from the ones that we are using in this class. There's no right or wrong in this case, it's just there are different standards. And LLM being LLM, it is probabilistic. So sometimes it would use the wrong standard. So you just kind of have to kind of watch out for that. All right, so continuing with this particular example, we do have one local variable, which is result. So result is a local variable. It is allocated by the callee itself. And right after the allocation for the local variable, register D, which is our stack pointer, points to the result, okay, or result as a local variable. So now we are going to use some labels, okay, so f underscore result is going to be 0 because it is at d plus 0, okay, so if you want to look at this as d plus 0, that's where it is. The next item is LVS, which is local variable size, which is f underscore result 1 plus because result is a pointer. I don't care what it points to, as long as it is a pointer, it is only going to be 1 byte wide. Okay. In this case, it is, I mean, it sounds complicated, but until we actually use it, we don't have to care, okay? Because from the C++ perspective, the type of result sounds really complicated, okay? It is a pointer to a struct node. But as far as assembly language is concerned, from the perspective of allocating the space for it, as long as it is a pointer, it takes 1 byte. That's all. Okay. I don't care what it points to, as long as it is a pointer, it is 1 byte. And now we move on to the first parameter, which is ppn. That's f underscore lvs 1 plus. This 1 plus is here because there is the return address that is pushed by the caller, and that's why we have this 1 here on line 30. In other words, when you look at the programs that we have written, that I have written at least, for basically half the semester, um, recognizing the pattern is important, but being able to explain each and every single line, why there's a 1 here, why does it refer to F result on line 29, those are also important questions to ask yourself, because once you understand why it works or why it is designed the way that it is, it's you don't have to memorize, okay? Because once you understand something, it's incorporated into your knowledge framework. So it's difficult to forget stuff, once you get to that point. So Pn is FPPN 1 plus because according to this kind of picture, but not a picture, Pn is 1 byte on top of Ppn. So now we have all the labels defined. Labels are nothing more than just an association between a symbolic name and the value that it is defined to. And that's all there is to it. Okay? Just because I define the labels does not mean that the stack is not properly set up, because labels do not affect runtime behavior. They are really just convenience features so that you don't have to just do all the counting and remember, oh, where am I supposed to find ppn? Okay, is it 1, 2, or 3? So it's just convenience. Yes, that is correct. So if now since this one only has one single local variable, I cannot illustrate it. So let's assume that we have two local variables, x, y. Okay. So whether you allocate x, whether x is below y or the other way around does not really matter, as long as your LVS accommodates both and the labels is not over, they're not stepping onto each other, then you'll be fine. Yeah, exactly. So as long as the labels point to distinct addresses, they do not overlap, and they're both covered by LVS, then you'll be fine. In fact, you can allocate more bytes than your local variables really call for. Even that is okay. Yes, as long as you consistently use the labels, you'll still be okay. Right. So in that case, the consistency has to do with the allocation versus the deallocation. As long as those two steps are consistent, then you'll be okay. All right. So now we do the allocation. Okay. So we have LDI B F underscore LVS, do a subtraction from the stack pointer. And I typically just do everything in a structural way because if I don't do it this way, I would forget. So LD BD increment D JMPB. Okay, there we go. So once again, line 39 to line 40 looks like a template because it looks like it's exactly the three instructions at the end of a function, but you still need to understand what they are representing, what they do, and why they work. Okay, because this is not the only instruction sequence to get a job done. I can give you alternate instruction sequences that can accomplish basically the same thing, and it does not look like this. Okay, so you have to understand what it is doing. Okay, and as long as the code that I provide to you does the same job, you do not want to fix it. Okay, you don't want to cross it out. It's like, no, this is not what you usually do in class, and it has to be like this. Okay, because if it has the same effect, it is not wrong. Yep. Well, if I tell you exactly that, that means I'm gonna. I cannot increment D, but I can fold getting the return address all the way before I even deallocate the local variables because I know where to find it. I always know where to find the return address. I can load it into register C, and then I can have a JMP C here, and then but these instructions will be somewhere else. Yep, yep. So that's why you have to track the registers, right? You have to track the registers. Specifically, the stack pointer is really important. Okay, where is the stack pointer pointing to? And if I use the stack pointer in some kind of calculation, like line 37, then you have to ask yourself, what am I doing with that line? Why am I changing the stack pointer? Every time I change the stack pointer, it is probably an important thing to understand how I'm changing the stack pointer and why I'm changing the stack pointer at that particular point of the function. Okay, so all of these they all come from the caller callee agreement. Okay, the caller callee agreement is really the most important document, I think, to understand when you want to really understand how these programs work. Okay, all right. So now we can go back to this code here. So when you are checking my code, okay, in the final exam, whether it's right or not, you can also, there are two ways to do this, okay? One way to do it is to do it in a structural way, which means when we get into a function, you check the allocation and then you skip a whole bunch of lines and check the deallocation at the same, right there, okay? And then you go back to the earlier point to continue the check, okay? So you do it in a structural way. If you do not do it that way, then my recommendation is have a checklist. Okay, so you have a checklist. Whenever you process a function, there's a checkbox for allocation of the local variable space, and there's a checkbox for the deallocation of the variable space. So if you check one, and then later on you get to the bottom of the whole thing, and the deallocation code is missing, then you know. Okay, having a checklist really helps because your short-term memory is, guess what, short-term. Okay, you can only track about 3 to 5 things at a time. So don't rely on your mind to remember everything, since you have the um, permission to bring anything that is on paper, including checklists and stuff like that. So try to make the most out of that permission. Yep. I would turn the caller callee agreement into a checklist. Okay, and if you want to kind of shortcut this, you might be able to use ChatGPT to do it. Upload the caller callee agreement document as a markdown file. Okay, and you scroll all the way to the bottom. There's a button that specifically let you copy and paste the copy into the clipboard, the markdown representation. Switch to ChatGPT, paste it in, and then ask ChatGPT to produce a number of checklists that might be applicable to go through the code and kind of find out what's wrong with the code. And you can even provide the context of I need a checklist to manually go through an assembly language program based on C code to debug it. Okay, so given that particular context, the ChatGPT may be able to give you a reasonable checklist based on the caller callee description. Yes. Um, that's up to you. You can upload a whole bunch of stuff, by the way. You can upload the opcode table. Okay, the opcode table can be uploaded. I think there are a few documents that describe the processor. One definitely describes how the stack is being used. Okay, how do we call and how do we return? You can upload all of those documents. Okay, they're all available to you. So anything that is linked from the Canvas shell is open OER. So that means you can keep a copy for yourself. You can upload it to ChatGPT, and then you can ask ChatGPT to generate like a summary, a checklist, and whatnot. I mean, it's you know, you do whatever you want with it. But I'm just giving you some suggestions. All right. So now we can go into this code. The first line here is to implement the conditional statement. So once again, it is a structure because this is a conditional statement. We kind of know what we need to do, right? So we have to say eval condition, and then somewhere there is a then branch. Okay, so here's the then branch. At the end of the then branch, we want to jump around the else branch. So we need a JMPI to uh, f and if zero. And then I typically just define the label like right away, f underscore and if zero. And then right under here is going to be the else label. This is where the else part is going to be. And if I want to be clear to remind myself what that code is for, I can even say, okay, this is where the else branch needs to go. Okay, in this case, we do have an else branch, so we're gonna stick some code over there later. So once again, it is structural. Okay, um, then I can now go back and evaluate the condition. The condition says there are two reasons to go to the then case. That means in order to go to the else case, we have to fail both of the then cases. So we'll see what we can do with it. Um, so we'll tackle the left-hand side first, which is checking whether what ppn is pointing to is null or not. If it is not null, then if it is null, then we go to the then case right away. If it is not null, then we're gonna have to check the right hand side of the OR. Okay, so that's what we need to do. So we need to get to what ppn is pointing to. So if you just listen to the description of the expression, it is not what ppn points to. Okay, so that means I need to figure out ppn first because I need to access what it points to. But before I get to what it points to, I need to get to ppn first. So that means I need the typical sequence of code to calculate the address first or the offset first. So we'll go step by step. This is the offset to the parameter from the base of the call frame. This is the address, and now this is the value of the parameter, and now this is what the parameter is pointing to. And the only thing I can use is JZI because that's check that. Oh wait, I cannot just do that yet. I have the AND AA first because otherwise it does not affect the flags. So now after the AND AA, if A is in fact a zero, then the Z flag will be set. In many other architectures, you can have a JNZ something to the else case, but in this case, I only have JZI. So now I'm going to have to jump directly into the then case, which means the then case also needs a label. And I think I stashed my code in the wrong place, unfortunately. Okay, there we go. So the then case needs a. Uh-oh, I made a. There we go. Okay. Yes. Okay, so this is correct. So now I need to define a label here, which marks the beginning of the then branch. Yep. I have to do the second condition. Hmm. Yeah, that's what I'm gonna do. Yeah, because every time you have a conditional branch, you have to ask, what if the conditional branch did not happen? So if I just have the code like this, then the conditional branch doesn't do a single thing. Or as in colloquial terms, it does not do diddly jack. Yeah, in both cases, it will go to the then case because JCI goes to the then case. If it doesn't happen, if we are still falling through to the then case, so it means it doesn't do a single thing. So we do need the right hand side of the OR to be where the cursor is. Okay, so that's actually necessary. It is not whether I can. This is actually what it needs to happen. What needs to happen. All right. So now what we're gonna do is to look at this and go like, well, it looks like this looks handy because we already have whatever ppm points to in register A, which is by itself an address to a structure, but we only want to access value as a member of that particular structure. So we go like, okay, that's kind of handy. So it's load B with node underscore value, which is the offset from the beginning of a struct node to the member called value. And then we just have to add, I think AB is fine because I don't need to keep A around anymore. Well, kind of handy to keep it around. Eh, eh, I'm debating whether to keep it around or not. Okay, let's keep it around because if I can keep it around for as long as I can, maybe I can still use it. All right, but the pointer to the structure is already in register A because it is whatever ppm points to. So now I just need a dereference to get to the left-hand side of the compare. So LD, BB, okay, now we're good. So B is the left-hand side. Now we can focus on the right-hand side and try not to overwrite register A because it is kind of handy to keep it around. So we'll see what we can do. Okay, LDI, we can reuse register. We can only use register C. I don't think we have enough registers to play with now, unfortunately. Yeah, yeah. Okay, so we'll see. So PN is loaded into C. That's just the offset. Now it is the address. Now it is PN itself. And we go like, I need another register. Nope, not anymore. Not anymore. So unfortunately, we don't have enough registers to play around. So register A can be reused, okay, because register B is actually useful. Register B is in the entire left-hand side, so I can only use register A at this point. Okay. Ugh, that's okay. Node value, and then we just do a add CA, and then do a LDCC. Mm, it's okay. I'm not going to spend the time to optimize the code. All right, so register B has the left-hand side, register C has the right-hand side of the greater than, okay? So once again, there are a few options here. Um, the idea is if B is greater than C, or if C is less than B, we go to the then branch. If not, we go to the else branch. So in this case, you can kind of reverse. There are several ways to do this. The I don't know which way is more direct now that we already have a label of then. So in that case, we can always just do a normal compare. But the compare is going to compare the other way around. It's going to compare CB, and then use a J. I cannot remember whether value is signed or not. So is unsigned. Yep, so if it's unsigned, it is JCI to F underscore then 0. So that means if it is not less than, then we need to go to the else case. So we have a JMPI, which is unconditional, to F underscore else 0. So there are several ways to do this. If you reverse the order of the comparison, then the JCI would actually go to the else case, but then you also need a JZI to also go to the else case. So either way, it's going to take two branches. There's no way to get around having two branches. But I just want to point out there are some alternatives here. All right, so now that the condition part is done, we then go to the then case, okay, and go like, okay, what do we do when we have the then case? Just a whole bunch of tedious stuff, okay? So I'm just gonna do it the really kind of tedious way without any optimization. Add AD, huh? Yeah, well, this part is not a loop, right? It's recursive. The recursive is the else part. Well, the exam has code that I wrote, so I might choose to optimize certain things. So you have to track the registers. I mean, the bottom line is you have to track the registers. Yep. But you don't have to optimize the code. You have to be able to track the code that might be optimized. Yep, that's a good idea. After each line, just write down what you think is in a particular register. So you just have to look back and say, okay, what was the last time I modified this register? And when it was modified, what did I put in that register? There's commenting and then there's commenting. Okay, the most useful kind of commenting in this case is relating the assembly code back to the C construct. Okay, so you want to use notation such as register B has the address of a parameter, or register A has the value of a parameter, or register B now has whatever that parameter is pointing to. Okay, so you want to document what a register has to your best ability to relate it back to the C code and C concepts. Okay, because that's when it will help you the most. All right, so continuing with this, okay, LDAA. So now we have PPN, and then we have to do it one more time. Now we have whatever it points to. And then on the other side, we have LDI, B, FPN, add BD, LD, BB, LDIC with node underscore P next, add CB, okay. And we just do a store CA. So that would accomplish line 18. Now we're moving on to line 19, okay. So if we're moving on to line 19, and if I want to, I'm not going to go there. We'll just reload everything. Just do the little quick and dirty. Huh? Yeah, exactly. So that's PN itself. Now we have to go to whatever PPN points to. That's, oh, cannot use register A. Add BD, LDBB, and then we do STBA. So now we are done with line 19 of the C code. Yes. We need, okay, so let's count the number of the references. So from the time I have the address of PPN, I need two dereferences, right? One dereference to go from the address of PPN to PPN itself, and then a second dereference to get to where it points to. Is that correct? And I have two dereferences. This is one, this is the second one. The second one is a store. Okay, all right. So I think it is correct, okay? But I'm actually secretly, now it's not secretly anymore, hoping that I make a mistake somewhere so the code bombs blow up and then we can get to see, how we debug the code. Woohoo! Yes. And people think that I actually have all of this code memorized in my head. You can give me a phone number and I can probably recite two digits out of all the digits. Is it 911 or 991 or is it 919? All right, so we are now done with line 19. Let's move on to line 20. Okay, so for homework, I'm just gonna say just do it a boring but sure way. Okay, just don't do optimization. Um, Go for the straightforward method, which is just a lot of typing. All right, so now that should conclude the then case, and we already have the JMPI here. If I did not do the code in the structure way, I probably would have forgotten that, oh, we are already at the end of the then case. We need to skip around the else case. I probably would have forgotten. So that's just me, okay? All right, so now we get to the else case. So the else case is actually, it looks horrible, but it's actually not as horrible as it seems. Okay, so we'll kind of do it the more straightforward way to do this. LDIA with FPN, add AD, LDAA, decrement D, STDA. So that would push PN on the stack. So once again, the caller callee agreement is important because you have to remember to push the second or the last argument first. Okay, so that's important. And now we are ready to push the first one. Okay. Yep. Line 80, 88. Nope. Nope. It's just the same PN. Yep. We are just passing the value of the parameter. Yep. So this is something, if you're listening to this and you're going like, okay, what are the concepts that I need to differentiate? So there's the offset to get to a parameter. There is the value, that's the address of the parameter. There's the value of the parameter. If the parameter is a pointer, there's also what the parameter is pointing to. Okay, so those are the four concepts that you kind of have to really differentiate. And when you look at this kind of code like here, you should be able to document on lines like 86, 87, 88, and find out, at the end of that instruction, what does register A contain? Is it the offset, the address of, or the value of a parameter? Yes, on the next one. So, okay, so let's see what we are dealing with here, okay? So the way we read this is unfortunately not going to be strictly from left to right. So the way we read this is we are trying to pass the address of the member P next of the structure that is pointed to by a pointer that in return is pointed to by ppn. So when you look at an expression like that, you hopefully can formulate that sentence in your head. Because once you can formulate that sentence in your head, that particular sentence is already telling you the dependencies of things. And whenever we say pointed to by, that kind of implies the use of a dereference. Yes, that is correct. Well, okay, not quite that, because we get to ppn first. Ppn is a pointer to a pointer, so we've dereferenced once. Then it becomes a pointer to a structure, which means we have the address of the base of a structure. We get the offset of p next, add to the address of the structure, and then we just pass that. We don't dereference. Yep. Hmm? That is correct. Yep. Yes. Yeah, the counterintuitive part of this is in C and C++, taking the address of something looks more complicated because you need the ampersand operator. But when you're implementing this in assembly language, using the address of something is actually easier because getting to the value of something means you need one additional dereference to get to the value. Okay, so just kind of keep that in mind. Okay, just little tricks, when you read the C code. All right. So I'm just going to do the whole thing. Okay. Register A is going to be FPPN1 plus. And then, yep. Aha. Y1 plus because of line, yep. Because of line 89. Because of line 89. The, the stack pointer originally was pointing at the base of the frame. And it's not anymore because we pushed the last argument already. So that means write down on your checklist, okay? What is on the stack? What have I pushed up to this point? How far are we away from the base of the frame pointer? From the base of the frame. Yes. Say that one more time. I'm not sure whether it will be an infinite loop or not, but you will definitely not, the code is not going to work the way it's supposed to. The label would still work because in assembly language it doesn't check the type. Yeah, but it doesn't know. It will mess up, but it's not going to report back as an error. The code simply will not work correctly. Yep. You could, but that doesn't make sense. But that would not be right because we have this one here not because of FPN, not because of where we find FPN as an offset, but because what we pushed took 1 byte. Yeah, but the label of FPN is meaning the offset from the base of the frame to where I find the PN. This one on line 892 is basically just saying, oh, we just pushed something that took 1 byte on the stack, and now the stack pointer is pointing to 1 byte below the base of the frame. So I don't know whether it would work or not. I think what would work, but it doesn't make sense, is LVS because LVS is one. But it doesn't make sense to put here because from the semantic of this location here, it's one not because of we have 1 byte of local variable. It is one because what I have just pushed was 1 byte. Yep, yep, yep. Go ahead. Yes, because you are okay. That's a good question. It's kind of philosophical. I like it. Um, until you mentioned it, I have not thought about putting bugs like that into the code. And and of course I have this whole thing recorded so that I can replay it. So I go like, what kind of questions should I use? Okay, let me listen to the whole lecture again. Yes, you assume the C code is correct, and the assembly code just have to do whatever the C code specifies. No, there will not be any logic or syntax error with the C code because I will test that. Sorry? In the TTPSM code, you can have syntax error or you can have logical error and so on. Yep. Hmm? You cannot specify really a hardware error in the code. Yeah, something like that. Well, thank you for contributing ideas, but those are easy ones, right? Yeah. If I if I just give you a bunch of things like the registers doesn't even exist, it's like, oh, you guys go like, great, this is easy, man. Yep. Yeah, go ahead. Oh, so I can name the functions and the labels in that series. So you see, label names like Jaja Bing or Jar Jar, or I can stick with just the droids. Just the droids, nothing else, just the droids. That would be kind of fun. All right. So now we have ppn in it. Okay. So we need to get the offset of node P next into register B, add register B to register A, or the other way around. I don't care. Um, and that's it. Yep, we good. Yep, and and then push the return address. Yep, dot 6 plus decrement D stda, and now we call the function we are supposed to be calling, which is f. Whoops. And then when it comes back, we have to increment the stack pointer twice because we have 2 bytes of arguments still sitting on the stack. And now we just have to load register A or store register A to wherever result is. Yes, question? Are you referring to the result of calling F here on line 24? Yeah, yeah. So you can, I guess you're asking, can we optimize it, right? Functionally, you do not, right? Functionally, you do not. But if you shortcut it on line 24, you have to shortcut it on line 22 because those two branches merge after the conditional statement. So if you do optimization on one, you have to remember to do the optimization on the other one so that on line 26, we just do nothing because the result is in register A already. Yep. Say again? I would not do that because you want a single point of return at the end of the function. The optimization is right here because the whole point of this sequence of instructions is to store the return value into the actual local variable result. So if we are optimizing and say we don't really need result as a local variable, then we can kind of ignore line 79 to line 81. And then on line 24, after the call, we are done. And then on line 26, we just do absolutely nothing because the return value is already specified in register A. So that's the consistency of optimization that I was talking about. So we are not going to do the optimization. I'm just going to do this as as straightforward as possible. In other words, whatever the C code specifies is what I'm going to do. So LDIB with F underscore result, add BD, STBA, and then when we get to and if, then we have to get result back out again. So yes, it is unnecessary, but it is not incorrect. Okay, so shoot for correct first. Okay, if you have time, then you can go ahead and optimize. AD, LD, A, done. Ooh, nice. I think it's done. All right. Well, yeah, go ahead. Hmm? So you have to compare that to the C code, whatever the C code is doing. I think I might have explained a little bit of what the code actually does. Oh, that's easy. Just put a halt instruction somewhere. All right, so let's go ahead and find out what this code actually does, right? So it says, if ppn, if what ppn points to is null, or uh, if whatever ppn points to as a pointer points to a structure where the value is greater than whatever pn as a pointer points to, or the value member of the structure that is pointed to by pn, then we go through the processing here. So what it is doing is trying to insert the nodes in order. It's trying to look through a linked list and find out where is a good place to insert a new node based on the value of the new node. So the time that is actually doing the quote unquote inserting is here. This is the actual insertion code. This is saying this is not a good spot to insert this node. Look elsewhere. And look elsewhere is the recursive call. So at the end of the whole thing, we'll go run the C code, okay? Because when I run the C code, we'll use GDB to look at how things are, which one is pointing where, and then the assembly code has to resemble what the C code is doing. Yes. Yep. It's good. All right. All right. So to debug this code means you need to know what the assembly code is doing to begin with. So we'll go ahead and do just that. So we'll do a gcc-g-o, what was the name? AR, ar.c, gdb ar, And I'm just gonna go. I will put a breakpoint on line 36 and run the code, and then we just print p first, okay? Or I should say print whatever that points to, p first. There we go. So whatever it points to has a value of 2, and then we say, what about what that points to? Okay, so we have to. There are two ways to specify this, but this is acceptable. Okay, and okay, and we want to dereference that. So it's 2 and 4, and then we just do it one more time. And the last one is 5. You can see how it is in order, right? We have 2, 4, and 5. But when you look at the actual N1, N2, and N3, let me go back to those lines. Nope, below before that. L10. Okay, there we go. So you can see that L1 is the one that has the largest value, N2 is the one that has the least value, and then N3 has somewhere in between. So the insertion is 5, and then the 2 and the 4. But the actual order, when you follow the P next pointer, is actually sorted. So we start with N2, and then we move on to N3, and then we move on to N1. So that's the desired, that's the actual result. Yep. The null pointer that you see here um, is really just, I have to initialize it with a value. You can think of this as a step of insertion sort. Basically, there's an array already, and you have a new value, and you're trying to figure out, okay, if I want to keep this list sorted, where am I supposed to put this new value? That's kind of what it's doing. Yeah. So you have to say, okay, so let's say your two is, mm, let's say 5 is already here. Okay. So if 5 is already here and you're inserting 4, then you go like, oh, this is already a good spot because I need to keep it sorted in an increasing order. But if 2 is already here and is the only thing here, and you're trying to insert a 4, that means, oh, okay, this is not a good spot. Let's move on to potentially you can be the thing after 2. So that's how we got the pointer to a pointer, because the address of the p next member of the node that contains a value of 2, that becomes the parameter ppn. So I'm passing the address of the member of p next of a structure along in the recursive call to parameter ppn, so that the call to f can now change a particular member of the structure that I'm supposed to deal with. But as I said, as long as the end effect is similar, then you got it. All right. So now is the moment of truth. And all I can think of is Jack Nicholson saying, "You can't handle the truth." Yeah, my mind works in mysterious ways. Annoyingly. Have you guys ever watched Ally McBeal, the TV series? Ally McBeal. That's the name of the character. Ally is Ally. McBeal is Mcbeal. Hmm? Yep. Before many of you were born. Thanks. Okay. I feel very mature. Ah, crap. Hmm? Dash? Oh, Oh, I did not know that. Neat. Okay, ar.ttpsm, and I'm gonna double check because of my favorite mistake of not saving it first. Mm, mm. All right, so it did finish. Nice. Okay, so let's figure out how to test this program, right? How do we know whether it works or not? So the first place we need to go is the assemble tab because we need to find out, where we have N1, N2, and N3. So we suspect that P first. I'm gonna have to write this down. So give me a second to pop up my text editor. Mouse pad. Come on, mouse pad. There we go. Okay. So I need to jot down because otherwise I would totally not remember. Um, so we need to remember we need P first. It should be the address of the one that has the least value, which is N2. So in this case, it should have the address of N2, which is hexadecimal 0A. And we know that it should be in order. So that means the next of N2 should point to N3. So that should be a 0, 8. So that means location, let's see, what would that be? 0A. So location 0A should have a value of 0, 8. And then the location 0, 8 should have a value of the last one, which is a 0C. And we should also see location 0C being overwritten by 0, 0. In fact, there should be a whole bunch of the 0, 0 store, but this one is we should see that. So that's what I can use to check whether the program works or not. And there are some other sanity check that you can do right away to see whether the program is even reasonably terminating or not. But we'll go ahead and kind of give it a check now. All right, so we are going to go to the end of this whole thing. Um, eh, sec fault. All right, so the first thing I would check is, did we get to the halt instruction? Which means, it is actually super easy to do because unless I forgot to do, no, 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 it's actually super easy to do because all you have to do is to do a control F and ask, where's the halt instruction? And no, it cannot find the halt instruction, which means the program did not work. Nice. Yep. So, okay, so it did not work. Woohoo! Okay, it did not work. Okay, now the question is, why is it not working? Okay, yes. Okay, so let's see how we can go through the debug process. Okay. Uh-huh. Yeah, you can kind of tell what it's repeating because I think it's calling the function over and over again, which means the termination condition is not met when it's supposed to be met. Um, all right. So what we'll do is we're going to track this down really step by step. Okay. Tedious process. Yep. All right. This is the return address back to the entry code. So we got that. And then FE is getting a 0 is, I mean, it even tells you the line number so we can actually tell what it is doing. Um, so we go back to line, what again? 136. Okay. All right. So Line 36, it is, hmm? Yeah, pretty sure. Yep, yep. I saved it. Yeah. Yeah, this one never reached the halt instruction, so I know it's not working. Okay, so this is this seems right, okay, because p first is the only local variable of main. F location ff is the return address, so location fe, being the only local variable of main, that's totally reasonable. So we got that, and then we move on. Okay, we are passing n. Okay, let me go back to the C code so that we can look at what the C code is doing. All right, so we are passing n1 as the address of n1 as the second parameter. So we push it on the stack. That looks good to me. So we should have the address of n1 pushed in the trace. So we want to double check that. Okay, so we just have to kind of scroll down, and 0c is pushed. Okay, that's good. And then we push the address of p first, which is also good. So we're clear with that one. And once we get in FB, which is the only oh, that's the return address. Okay, so we're not in the subroutine yet. So now we're in the subroutine. Um, and over here, I'm just looking for the next store instruction here. So it's storing a 00 into 0C on line 66. So now we look up line 66 and we go like, is it what is it storing? This is corresponding to, let me go back to the C code so you can see what C code we are doing here. I think it is doing this here. Let me just check. Yep, it is the then branch. So it's storing whatever ppn is pointing to the next of whatever pn is pointing to. So pn is the address of n1. So the next, which is the first byte of n1, which is zero at location 0c, that's correct. Ppn is is the address of p first, which was initialized to 0. So the right hand side being 0 is correct. And this side being 0c is also correct. Yep. Okay, so we'll get to that. All right. So you're analytically checking the code to see, okay, so all right, so we check the okay, we'll check the code in here. All right, so we are pushing pn by itself. This is the offset, this is the address, this is the value. We push it on the stack, so we are good. This is the offset to ppn. This is the address of ppn. This is where ppn points to. This is what ppn points to. Which this is the value of ppn. The value of ppn itself is a pointer to a pointer. So you are correct because I'm missing one LD right here. Yes, good job. So that there's a missing one here. So the so you look if you look at the number of dereferences here, there's one dereference to go from the offset to the value of ppn. This is obviously one dereference. The third dereference is here. So there should be three dereferences. Without this one here, I only have two dereferences. Or, well, the address of cancels out the last dereference. So that means the correct code should have two dereferences, but my original code did not have line 95, so it's missing one dereference. The, yes, yes. So in terms of notation, okay, so let me kind of show you guys the equivalent notation here. So in terms of notation, let me just use PN here. This is exactly the same thing as, so that's why there's a dereference here. All right, very good. So we're going to save the file and then check it again. But if you did not tell me where the bug was, I would be going through the whole process, really kind of step by step. Yep. I have done this for years, dealing with my own bugs. Yep, that's the hold instruction. And then we go back and check the memory write. This is not the definitive one. Okay, this is one of the definitive ones. So we check this against what we said it would do. So 0A getting a value of 0.8. There we go. 0.8 getting a value of 0C. There we go. And oh, okay. Do, 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 do. Yep, there you go. 0A gets 0C. Oh, no, that's not. That got changed later. So the last update is what counts, right? Because I think the last update was that one. Okay, we can check that. Okay, so we go here and we are looking for 0A gets 0.8. Yep. So that was the last update. 0C gets 0.0. All right. Yep. So right here. All right. So how was it okay, the process? Okay. Did you guys debug this program like you really kind of step by step, or did you try to do what I just did? It's like, let's write the whole thing and keep our fingers crossed. Exactly. Yep. You know, hmm being able to describe how you approach programming actually may be helpful in a job interview. Because I think these days they want to know how you think, how you write your code, how you structure your code, instead of just trying to see whether you seem to know what they think you know or not. Are they using AI to do interviews? Do they? I don't know how, but it becomes hackable because then if they figure out how the AI on the employer side is quote unquote programmed, then you can specifically kind of target that. But that's why you want to approach smaller companies because smaller companies may not have the volume of applications where they have to rely on AI to do things, nor do they have the faith in AI to rely on AI. All right. How to get your foot in the door, okay? Particularly with the state government. So you want to go to, huh? Yeah. Uh, yep. And for the most part, now this part, I know most of you are not thinking that this is important, but I think it's actually important. Um, you might already be qualified to be an IT technician in the state of California. Yep. Yep. The reason why the state is an interesting choice is because not it's not because of the pay is kind of really way below industry. Is the job security and your retirement security because the way they calculate your pension is predictable. It's in the contract. So if the contract says, okay, you have, I'm just pulling numbers out of thin air, okay. So if they say 2% at 60, that means if you work up to 60 years old, then for every year that you work for the state, it is 2%. So that means, let's say, you graduate from Sac State at the age of, what is the typical age? 22, 23? Say 23, okay? So 23 and you work until you're 63, so you have 40 years service credit, right? So that means if your contract says 2% at 60, that means you multiply the number of surface credit, which is 40, times the age factor, which is at least 2%, that's 80%. So now the question is 80% of what? It is not 80% of the running average of your entire employment history with the state. It is 80% of the highest paid 3 years or so during your entire employment. In other words, you can stay at a very low pay for like 30 years, okay? And then you just go like, hmm, got a major, promotion. You get your pay up all the way, and then you stay with that job or that title for 3 years, and then you go like, this is way too much work. I'm almost ready to retire. I'm gonna go all the way back to the earlier, easier job until I retire. You can do that. Yes. Well, I mean, we can all go out and then it's entirely possible an asteroid hit us like now. Yeah, but it's plannable. Okay, it at least you can plan for it, right? Which is a big thing. Okay, if you work for Intel, okay, imagine this scenario. You're working for Intel, okay? So you guys might go like, who in the right mind will work for Intel at this point? You're correct, okay? But think back, say 10 years, okay? So 10 years ago, people are going like, oh, working for Intel is the best thing ever. And then you yes. And then they just chew you up. They use it like a light bulb. It's like, oh, one just burned out. We just change the light bulb because there's a whole line of light bulbs lining up to be the next light bulb. Yep. 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 And they make sure that you are like a light bulb. In other words, if you try to diversify, it's like, oh, okay, I've been working on this aspect of the circuit for 10 years. Okay, I know everything there is to know about this. I'm going to work on those things. Can I do something else? They will say no, because they want to pigeonhole people so that, what you do is well specified, which also means now it's easy to replace you. If you can take on multiple hats, okay, I can work on signal processing on this project. I'm working on instruction optimization on this project, and I'm working on FPGA design on this project, and I'm good at everything. And you decide that, I'm just gonna go work for AMD now. They go like, okay, how do we find a place replacement that can work on all of these other projects? It's much easier to manage things when they say the only thing you're going to work on is this little niche thing. And I cannot tell you because I've never worked at Intel. I worked at a small company before I started teaching. I was employee number 12, I think. I was the only software engineer of the entire company. So I had to do tech support. I had to maintain the GUI interface of the compiler. I have to maintain the parser of the compiler. I have to maintain the library, function, library of whatever the compiler links with. I have to handle customer calls, the technical ones. Whenever they come up with a new board, I'll be the first one to go like, the hardware engineers will just drop it on my lap and go like, tech, make it go. And sometimes, not always, but sometimes there'll be like a hardware design issue, so it doesn't work the way it's supposed to, and there's nothing I can do in software to make it work. And then they will always insist it's a software issue tag. We did our job. It's your job now. So that's how I learned how to work with hardware, how to read schematic, how to, do the logic sim thing that we saw, right? And how to read the power equations so that I can actually diagnose their design problems. Then I can hand it back to them. It's like, I think this is supposed to be an and not an or something along that line. No, because I was wearing many hats. Okay, and no, the owner of the company. This is a privately owned company, tiny small company. The owner of the company will not fire me. Okay, I'll tell you why. Because he graduated from Berkeley with a master's degree in physics, and I think now this I can be wrong, but I think he thinks he's the smartest person in the entire world. Does that remind you of a certain politician? Okay. And he thinks, okay, now I think he's overrating me. He thinks that I'm the second smartest person of the company. He so he enjoys, okay? So it is his pleasure to argue with me on technical stuff, okay, of all kinds and win the argument. So I wouldn't trust that cookie. But there was one time I was really frustrated, and I was tired. It was lunchtime and I was tired. And then he said, Tech, why don't we do it this way? I think this is a better idea. And then finally I said, Norm, we'll just do it your way, okay? It's fine. We'll just do it your way. And then he said, his face went red like a certain politician. And then he said, F you, Tech. I go like, what did I do? I just agreed to what you told me to do. Okay, it's because I did not give him resistance to prove that he is the smartest person of the company. So I think that, along with a few other things, was the reason why I don't work there anymore. You know, or sometimes it would last the whole day. I would get nothing done the entire day, and he doesn't mind at all. Yeah, so I made the mistake of just being frustrated and showing my frustration and say, well, we'll do it your way. I should have said, you're so smart. Oh man, I did not think of doing that. Let's do it your way. And and then I can just kind of go back and really do the things that I enjoy doing. So anyway, that's yeah. Hmm? It helps to regulate mind. Yes. Well, if you can apply for IT technician, but there's one thing that you have to remember. It takes 9 months to process your application. So you have to plan way ahead of time. Don't expect anything back, but check anyway. But don't expect anything back for a long time. Okay. Well, okay. So the so-called exam is not like an exam like in a college setting. Self-assessment. It's a self-reported assessment thing. It's like, so do you have experience doing this? Do you have experience doing that? Blah blah blah, and so on. Yep, yep. But that's only applicable to but it's only applicable to each position that you apply to. So if you apply to 5 different positions, it's okay. I take it back. It's not 5 positions. It's 5 classifications. So it's based on classifications. So student assistant is one classification. IT technician is one classification, and so on. So with you have all taken. By the time you apply to these jobs, you would have taken at least 15 units of classes that relates to IT. All programming classes are considered to be IT related. So that means you will be qualified to be an IT technician. It does not require a bachelor's degree. So you can be an IT technician while you are a student, undergrad student at Sac State. I know people who manage Linux servers, and they admitted to me that the work is usually mostly done by student assistants. But you want to make sure that you know when the surface credit starts counting because I'm not sure whether student assistant counts or not. But it's a foot in the door because if you perform, no matter how tedious the job really is, and you go like, okay, I'll do it, and I'll do a good job. And when there's an open position, those people who are around you, they will give you assistance. They will tell you all the inside information of how to. That is partially true. It depends. No, no. Okay, so the way to get out of the state is something like this. It doesn't really relate to IT. Well, actually, it does relate to IT too. Um, so let's say you work for IT, okay, and then you work your way up, and then at some point you work for you're at a position to manage the purchasing and the contract management of things, right? So now you know all the inside information of how to be a successful contractor for the state, how to fill in the applications to become a contractor, who to contact, what you need to mention in the contract, blah blah blah. So you just go like, okay, I'm quitting my state job and I become a consultant to help contractors who want to get a contract with the state. I know a few people who did that. Sorry. Yep, yep. But you know the ins and outs. Sorry? Yeah, well, but it's a more technical kind of lobby because you're helping contractors and vendors to work with the state to get the contracts. Yep. Yeah, you guys can go. Yeah, go ahead. There are a lot of influencing around. Uh-huh. Yeah. So 9 months is not a bad estimate. Oh, okay. Yeah. Yeah, but it's a good place where you can, go to Sac State, get your bachelor's degree while working too. Yeah. Hmm. Yep. But that's not time wasted because all that time that you spent debugging, looking at your own program to check whether you did something correctly or not, that's actually one of the best way to study. Because you're re-examining things that you think you already understood, but now you look at the trace, you can see that, oh, okay, that part works, this part works, this part works. Hey, this part is supposed to do this, but it's doing that. So I think it's the best way to study, and that's it's also the best way to really understand what is in the register. Do I have the offset, the address of, the value of, or what it points to? Because now you can actually see it in the register. But thanks for contributing. Yeah.